Hello everyone, my name is Hongnan Lin. I'm glad to present our paper, TacTex, a textile interface with seamlessly integrated electrodes for high-resolution electrotactile stimulation, on behalf of the co-authors. Textile-based haptic interfaces are emerging as a groundbreaking method to integrate haptic feedback into everyday items, including clothing, furniture, and vehicle interiors. Electrotactile stimulation employs surface electrodes to activate nerve endings, thereby replicating sensations such as touch, vibration, pressure, and complex spatial temporal patterns. Despite the promising potential of combining textile-based electrotactile interfaces, it poses a substantial challenge to fabricate a high-resolution and large-scale textile electrode array and control it to accurately convey tactile sensations. To overcome these challenges, we introduced TacTex, a textile-based electrotactile interface to deliver high-resolution haptic feedback and touch tracking capabilities. In the forthcoming sections, we will delve into the 4 key components that constitute the TacTex system, illustrating how each contributes to its overall functionality and performance. TacTex features an innovative textile electrode array, leveraging multi-layer weave. As shown by the design of an example TacTex textile, in which the warp electrodes are separated from each other by non-conductive warp yarns, and the weft electrodes are separated from each other by non-conductive weft yarns. The weave structure can be adjusted in various ways to meet different needs on electrotactile sensations and visual appearance. The results showed that we can achieve electrically reliable textile arrays that no short circuits were identified through deformations. We evaluate TacTex textile structures, especially their ability to preserve electrode integrity under typical usages. These textiles were crafted from commercially available yarns using both 2D and 3D weaving machines. While 2D weaving machines are widely accessible and can be repurposed for 3D fabric production, 3D weaving machines offer the dual benefits of higher efficiency and superior mechanical properties. To gauge the durability of our textiles, we focused on the short circuit rate, denoted as R. This rate represents the ratio of unintended connections, or short circuits, between the warp and weft electrodes over the total number of electrodes. We simulated real-life wear and tear by subjecting the fabrics to repeated stretching, shearing, scratching, and bending. This was done 1,000 times in each direction, employing specialized motor-driven equipment to ensure consistency. And the findings are promising. Our textile arrays stood up to the test, maintaining electrical reliability with minimal short circuit detected post-deformation. This indicates that TacTex textiles are not just conceptually sound but are also robust for everyday use. We developed an efficient technique for connecting textile electrodes with contact pads on a tailor-made flexible printed cable with anisotropic conductive adhesive. This method allows for connection to the driving circuit without introducing any rigid or bulky components. The end result is a reliable and durable connection that readies the TacTex electrode array for action, maintaining the flexibility essential for applications. We designed a driving circuit for a 512 electrode array. It comprises an adjustable high-voltage constant current power supply, a sensing board, and 16 sets of controllers paired with tri-state switches. The power supply regulates and maintains the current output in changing load conditions, with voltage output up to 350 V. The controller operates switches to spatially and temporally control electrical stimuli on the textile, while simultaneously monitoring voltage changes to capture real-time touch events. A switch can connect an electrode to either the ground, a high voltage, or place it in a high impedance state. The controllers control switches to adjust stimulus location and waveform timing. The sensing board compares voltages measured from the sampling resistor to a reference value. If the values are the same, the activated pair of a high-type electrode and a low-type electrode is not touched, and vice versa. By manipulating the activated electrode and pulse waveform timing, TacTex can stimulate a broad spectrum of haptic effects useful in human-computer interaction, including 4 types of sensation qualities, 10 static patterns, and 10 dynamic patterns. TacTex uniquely activates a pair of parallel anode and cathode electrodes at a time to achieve a localized line-shaped tactile sensations, essential for composing spatial temporal patterns. It's possible to change the orientation, position, and distance of an activated electrode pair. This activation method emerged from our early design iterations. We also explored 2 other activation methods that proved less effective. The first was activating a pair of perpendicular anode and a cathode at a time. The second was activating an anode and multiple cathodes perpendicular to the anode. Neither of them yield reliable concentrating sensations. This waveform features pulses organized into bursts, characterized by specific parameters: pulse width, pulse period, number of pulses, and burst period. When we employ multiple electrode pairs, the waveforms maintain identical shapes but are staggered over time. We refer to the number of electrode pairs as the channel number, with the time offset between them termed the inter-channel period. When electrotactile pixels within the same burst period are activated, the user perceives them as simultaneous. Our design incorporates 3 separate pulses per burst, avoiding the use of a single, prolonged pulse on one channel. This decision is grounded in research, specifically aimed at minimizing the risk of discomfort. Studies indicate that pulse widths exceeding 200 microseconds can lead to pain and shock. Electrotactile pixels activated within the same burst period are perceived as activated together by the user. The intensity of these pulses remains constant for each individual, set between 0.5 to 3 mA, based on thresholds determined during our calibration experiments. Moving on to the types of sensations our interface can produce, we achieve 4 distinct qualities: pricking, caressing, tapping, and pressing, by tweaking the pixel properties and burst parameters. Pricking is a sharp, concentrated sensation affecting the surface layer of the skin, while caressing provides a gentle, superficial feel. Tapping offers a muffled yet deep sensation, and pressing delivers a sustained, deep pressure. Regarding spatial patterns, our system, TacTex, can generate a variety of static designs using warp and weft pixels. In these configurations, while the waveforms are the same in shape, they are temporally staggered, as shown in Figure 6. Each pulse period sees the activation of all electrode pairs. Furthermore, TacTex can produce dynamic patterns by updating the static ones sequentially over time frames, with each frame lasting between specific durations, allowing for a consistent activation of pixels akin to the static arrangement. In our study, we evaluated the TacTex interface's effectiveness in eliciting 4 distinct sensation qualities and in displaying 10 different static tactile patterns as well as 10 tactile animations. We also assessed the level of pain associated with electrotactile stimulation. In our analysis, we calculated the accuracy of sensation qualities, static patterns, and dynamic patterns by averaging the responses from all participants. We also determined the balanced accuracy for each category. Our findings showed that the accuracy for sensation qualities was approximately 78%, and for static patterns, it was close to 88%. The average reported pain level from electrode stimulation was relatively low, at 2.75, with a standard deviation of 1.60. TacTex, our advanced touch tracking system, shares its hardware with the electrotactile stimulation functionality. This integration is achieved through time division multiplexing. TacTex is capable of touch detection by rapidly scanning across warp and weft electrode pairs. The electrical waveforms used for this purpose are specifically designed based on user experiments to avoid inducing tactile sensations. The system determines touch by detecting changes in the state of activated H-type and L-type electrode pairs through the sensing board. A touch is confirmed when both warp and weft electrode pairs indicate a state change, allowing TacTex to accurately map the touched areas across the textile surface. We conducted a 2-point discrimination study to examine the spatial resolution of the TacTex in touch tracking. Our findings revealed that at spacings of 1 and 2 mm, the tips were indistinguishable by touch. However, when the spacing was increased to 3 mm and beyond, the tips became distinctly perceptible. This study highlights the TacTex's ability to differentiate between close contact points, showcasing its fine spatial resolution in touch tracking. We embarked on a series of experiments to refine the touch tracking signal parameters, with the goal of making TacTex track touch seamlessly without interfering the intended electrotactile effects. Imagine a symphony where a rest is a pause in the music. Similarly, in our interface, sensing pulses might introduce such arrests or pauses within the stimulating pulses. If these pauses grow too long, users start to detect them, and the immersive tactile sensations we aim for gets interrupted. But it's not just about the length of the pause. Even if a sensing pulse is brief, if it is too strong, it becomes detectable. We conducted 3 carefully designed experiments to address these aspects. Experiment 2 delved into how long intervals could be without users noticing a break in continuous haptic feedback. Experiments 3 went a step further, examining the detection threshold of intensity-related parameters, which is pulse period against pulse width, for various scanning methods. Experiment 4 evaluated the disturbance caused by touch tracking to haptic stimulation. The results show a clear trend. As pulse width increases, the frequency at which participants detect stimuli decreases, but only within a certain range. Below this range, stimuli go unnoticed even at the system's maximum frequency of 250 kHz. Above it, even at a low frequency like 1 Hz, the stimuli become perceptible. Finally, experiment 4 was to assess whether touch tracking interferes with the intended haptic sensations, spanning across 4 haptic qualities, 10 static, and 10 dynamic patterns. Participants experienced a haptic effect on their index finger. Subsequently, they placed their finger on the textile, which then engaged in multi-touch tracking to replicate the same effect to the finger. The participants answer a yes or a no to whether the 2 haptic effects were identical. The experiment was set up using the shortest pulse width and pulse period our system supports, based on insights from previous experiments. The findings were unequivocal. All participants reported no difference between the designed and actual haptic effects during touch tracking. This tells us that the TacTex interface delivers consistent haptic feedback, even while tracking multiple touches. We developed 4 prototypes, implementing TacTex's tactile sensing and actuating capabilities, and tested them within our team. We envision that the expansive TacTex fabric, paired with a projector, offers enhanced interactivity. This large-scale material enables users to enjoy a novel and highly engaging gaming experience. The desk cloth used on a working table can stimulate an additional keypad with tactile feedback to key press. Text material yoga mat elevates the user's workout experience by providing interactive assistance. Strategically placed electrical stimulations assist in correcting posture, while consistent discharge patterns serve as both a timer and a source of motivation. TacTex can seamlessly integrate with everyday objects, such as pillows. Users can experience a gentle awakening as the alarm clock triggers TacTex to generate a soothing stimulation waveform. This stimulating feature also elevates the music experience, offering a more immersive sensory journey. For more details, please refer to our paper.